You've had a chance to try several of these kinds of problems where you say, hey, I have a force that's causing something to accelerate. Okay, we could have even done those kinds of problems here, like what other force would I need to add up so that that body wouldn't move or change its motion? If a body is not changing in its motion, then all the forces are balanced. And that's its own kind of problem where you just have to add those up like vectors so that they add to nothing. And I'll work an example out for you in the problem that sets it up fairly straightforward. But what we do want to say is what kinds of forces are there, and let me draw those out. Here's a set of common forces that you may run into in different kinds of work problems. Now let me make this a little bigger so we can see what these all look like. Okay, and let's talk about them really quick. One force is just going to be a body's weight. Now on Earth, our weight is just our mass and then being accelerated. Remember, force times or mass times acceleration is a force. That acceleration is always the same pretty much uniformly. I mean, there are small differences on this Earth, and that's usually that 9.8 meters per second. The weight is always going to be pointed downwards. I'll draw us a picture of these here shortly. Normal force. Normal force just means that if I set something on a table, okay, if I set something on here, the force that is required to hold that object up is called the normal force. If you sat on a table, your weight would be down on the table, and the table's force up would be the normal. So notice it's got a W, a weight function in there. Now that's not always going to be nice and straight, so I'll have to get into why we're putting some of these cosine angles in here. Another one that's going to be important is going to be called a force. So if you start to now lift some object up on a ramp, if that object is sitting there, all of its weight is no longer straight down on that board. Some of it's actually encouraging that force is encouraging that object to slide down it. And so that's how these break apart. The part that's pushing into the board itself is called the force perpendicular. That's the weight times the cosine of this angle of how much this is, this is leaning upwards. Whereas how much is pulling it down the hill is called the force parallel, and that's what's going to cause it to slip. So if you parked your car on an icy hill, that's what's going to cause it to slide down. The force of friction is very common that we would use. Force of friction is just some fraction times the weight that you express against the surface. So if you're standing there, it is your weight. If you start to lift that up on a curved sort of a hill, then it's going to be whatever your force is pushing down into the hill, that force perpendicular, that normal force, times some fraction. So in other words, if this hill is kind of slippery, and it takes 1/10 the force that it would to lift you, to slide you, then if that's being applied, you would start to slide. A couple of other kinds of forces that might be there, and they won't occur in all these kinds of problems. There's a force that springs provide, and it just depends on how much you squish the spring. So it's some constant times the amount you've squished the spring. Like 3 newtons for every meter you squish it. Like a slinky would be about 3 newtons for every meter that you stretch the slinky. If you take something and are swirling it around your head, or you're trying to take a curve on a road, it's going to take a force to keep changing your motion, and that's called force centripetal. That's whatever your velocity is that you're going around, or how fast you're swinging something around. You know, if you swing something around your head, it's taking a force to keep it swinging. Okay, and so that's going to be the velocity over centripetal this is supposed to be an R. Okay, over the radius of that turn. The buoyant force, you guys in California know this all the time. You see these balloons floating, and the force of that balloon being risen up is dependent on the weight of that space. Whatever you're displacing, if that has a weight, that's how much force is pushing it up. If that force of that weight of the material you're displacing is more than the weight of you, then what's going to happen is that air will want to come down and sink underneath you, and it's going to push you up with a buoyant force. Okay? The buoyant force is whatever the weight is of what you're displacing. So if I jump in the tub and I have 1 cubic meter of body, or let's say 100 liters, whatever 100 liters of water weighs is what's going to lift me up. And there's some last minute ones too. That torque, if you're trying to fix an object with a force or a wrench, the longer that force is from the point that it turns, the distance from where you're turning, your torque is going to increase. Sometimes we might talk about tension on a rope, and that what you have to do to figure the tension is what's on the other end of the rope. You say, is there something hanging there? It's one of these other kinds of forces. So all of these are going to be available for if you have to run into one problem. Most of what I want you to do is just to recognize, is that a buoyant force, or is that, you know, some other weight, or is it a parallel force? And so today, when you take a look, we're going to actually have you choose some, just like we were choosing the right kinds of equations. I want you to recognize where those forces act. So that's what we have as an assignment right now.